Thanks for the introduction. It's a great pleasure to be here, to see many friends. Thanks for the invitation. I'm glad to be affiliated with Academic Sinica from now. I hope this is a good start of long-term collaborations. So the title of my talk is Mathematical Theory of General Relativity, and of course I'm a mathematician. And I hope by the end of my talk I can convince you there are actually a lot of very interesting problems in general relativity that is worth the investigation of mathematicians. Okay. So Einstein founded the theory of general relativity in 1915, so more than 100 years ago. And he actually built on the theory of special relativity, okay, which was actually established in 1905, 10 years ago. And special relativity is based on two axioms. The first one is the speed of light is a constant. And the second one is nothing travels faster than light. And this actually, just these two simple axioms actually address a major puzzle that had baffled physicists of Einstein's time. Because at that time, we didn't realize how light propagates. Okay? So at that time, there was actually a hypothetical ether that was created, just a medium for light to propagate. But once these two axioms were proposed, you just don't need any ether, any hypothetical ether, and you can just explain light propagation very easily. And Einstein actually values this kind of axiomatic approach. And in many of his essays, he actually compared this to the Euclidean geometry in pure mathematics. And in fact, special relativity can actually be considered as a new Pythagorean theorem. Okay? So by Pythagorean theorem, I mean the following. Suppose you have 2 points on the plane, O and P, and you can use different coordinate systems, so x, y, or u, v, to describe the distance of these 2 points. Okay? And let's suppose this point O is always in the origin. But now you can see that it's x0, y0, and u0, y0. They may be very different, okay, although they represent the same points. However, this formula, that's a Pythagorean theorem, because you have a right angle here, right angle triangle here, you have another right angle triangle here. So Pythagorean theorem tells us that this is always the same. Okay. But in the case of special relativity, you want to describe the difference between two events in space-time. So let's say you have one event O and the other event P here. And you can describe these two events using different coordinates. Or physicists like to use observers. Okay? But really, when they talk about observers, it means you set up a coordinate and you try to describe these events. And let's say you have a coordinate system xt here. X will describe a space, and t describe time. So space-time coordinate, x and t. And let's say, one of the event is at the origin, so x equals 0, t also equal to 0. And the other event, according to this observer, the coordinates are x equal to x0 and t equal to t0. But you can see this x0, the space coordinate, and t0, the time coordinate, they depend on the observer. Okay? So different observers come out with different space and different time. Okay? However, according to special relativity, this quantity here is always an invariant. And this is what is called the Lorentz norm. Okay? So no matter which coordinate system or which observer, when you look at these two space-time events, they come out with different x, different t. If you compute this quantity here, it's always the same one. Okay, so this is an invariant. Okay, so you can say this Lorentz norm is an invariant, just like the one in Pythagorean theorem is an invariant independent of coordinate system. So any two observers record the same Lorentzian norm between the two events O and P. Okay? I mean, Einstein used to use different stories like trains or carriages to describe all this. And when you look at them, but it all comes down to this formula here. Okay? But when it comes to general relativity, Einstein actually needs more mathematics. So in particular, he needs Minkowski. Minkowski is actually Einstein's teacher at ETH. And of course, Einstein came up with this special relativity, but it was actually Minkowski that formulated this space of special relativity as the Minkowski space. Okay? So it's really the three-dimensional space XYZ that we're familiar with time coordinate, that is T here. Okay? And he considered this four dimension as a single space, a space-time. Okay? And also Lorentz talked about the isometry group of this metric here. And of course, you also need Riemannian geometry, which was invented by Riemann about 50 years ago. And also tensor calculus, which has been used in the formulation of electromagnetic theory by Maxwell. Okay. And general relativity, in Einstein's theory of general relativity, so the space-time, okay, is again a four-dimensional manifold, but it only resembles the Minkowski space locally. Globally, there is actually a metric. This G here, this is so-called Lorentz metric. Okay, so this is a four-dimensional space that is equipped with a Lorentz metric. So this means that a signature is actually the same as the signature of the Minkowski space, so -1, 1, 1, 1. But this G here is no longer a constant or flat metric. Okay, and in fact, the derivatives of G or the second derivatives of G will form the curvature, and the gravity is actually encoded in the curvature of this Lorentz metric. And it's actually governed by the Einstein equation. So this is the Einstein equation, and this is the equation for tensors. Here this RIC is actually the Ricci curvature of G. It's a combination of second derivatives of G. And R is the scalar curvature of G. It's just another combination of curvature of second derivatives of G. And the right-hand side here is the energy momentum tensor of matter density. So it depends on what kind of matter you use, maybe electromagnetic field or scalar field. But you can see the left-hand side is computed from gravity, and the right-hand side is computed from matter field. So this is a theory that unifies space, time, and gravity. And in this lecture, for simplicity, I'll just assume t equals 0, okay? So meaning that there's actually no matter. So we'll just consider equation for gravity. So when the right-hand side is equal to 0, then some simple algebra will actually imply this Ricci curvature is equal to 0. So is this a scalar curvature. So the equation is really the so-called Einstein vacuum equation, so abbreviated as EVE. Okay, so it's just this Lorentz metric here, and you compute this second derivative, actually quite complicated, so that's why I don't want to write down here, but a combination here, and that will give you the Ricci curvature. But the important thing here is that this equation is invariant under coordinate change. Namely, you can use any different coordinate, and in this case, you can even use some curved coordinates. You know, unlike these Cartesian coordinates that we just mentioned, you can use any curved coordinate to describe it. And if your Ricci curvature is equal to 0 in one coordinate, then it has to be equal to 0 in a different coordinate. Okay? And this equation is actually as fundamental as the Laplace equation. So this is one that we are all familiar, since multivariable calculus on the three-dimensional space. And this is the equation that governs Newtonian gravity. But this EVE here is somewhat more complicated than this Laplace equation. So it's actually a system of 10 unknown functions and 10 equations. And it's also very nonlinear. So it's extremely complicated. But somehow in just a few months, Schwarzschild, I mean, he was actually in the front line during the First World War. He actually discovered the first non-trivial solution of the Einstein vacuum equation. Okay, so I'll consider this Minkowski metric as a trivial solution, because that really just corresponds to, G is a constant, you take second derivative, and everything vanishes. But this is the first non-trivial solution. And I mean, of course, you have to make some ansatz. In this case, just assume everything's spherical symmetric, and at the end, you just come down to solving an ODE that is actually integrable. And it has actually a very nice form here. So, for example, the Minkowski metric, we know the Minkowski metric is really just a one-time dimension, and the other three are R3. But you can actually choose the spherical coordinates to describe the flat metric on R3. Then you actually has this form here. So this part here is still the time dimension. It has a negative signature. And this part here is really just the flat metric in R3 in spherical coordinates. But in this coordinate here, Schwarzschild's solution is actually very simple. Really, you just change this -1 here to this expression, and change this 1 here to this expression. Okay? And in particular, when R, so R still represents somehow the radius. So when R go to infinity, this term vanish and this term vanish. Okay? So it will mean that when R go to infinity, this is actually approaching R3, approaching Minkowski metric. So this means if you go out to infinity, you actually become very, very flat. And so there's actually almost no gravity. So this is considered to be an isolated system. So isolated gravitating system. So you have gravity in the center, but gravity becomes much weaker when you approach infinity. And you eventually get closer and closer to the Minkowski metric. So this is actually very simple. This is something that you can actually give to maybe first year, second year undergraduate student. Just reduce to a second order ODE that is integrable. But this solution appears to be undefined at R equal to 0. Okay, so you can see when R equal to 0, you have something blows up, and R equal to 2m, right? So here again, R equal to 2m, you have this blows up. So this appears to be undefined. Okay? But just remember, I mentioned that this equation, Einstein equation, is invariant under coordinate. Okay? So you can actually try to choose a different coordinate to change it to a form that has no singularity. And turn out this is actually the case. Okay? So you can choose a different coordinate system, and you see that this singularity R equal to 2 is R equal to 2m is actually removable. Okay? You can choose a different coordinate system to write it in a different form, so that all the coefficients are just bounded functions, regular functions, smooth functions. Okay? So I'm not going to write down this coordinates change here. But I mean, just emphasize this is a geometric equation, so it's independent of a coordinate system. However, when R equal to 0, this actually represents true singularity. Okay, so this is where, for example, curvature actually blows up. Okay, it's totally undefined. Okay, I mean, although this expression has some undefined coefficient, but you can actually compute the curvature at R equal to 2m, and you'll see that at R equal to 2m, everything is fine. Okay, and then you can just go ahead to try to change a coordinate system, and you will see that, the finiteness. Okay, so it turns out Schwarzschild's solution is actually a black hole solution. Okay, it actually represents a black hole. Of course, this term of black hole was invented much later, until the 1970s, Wheeler. And R equal to 2m actually represent the horizon. Okay? So once you get past the horizon, so this is when you have a particle here. Once you get past the horizon, you enter the region of r equal to 2m. You will never be able to escape from the region. So in particular, light will never be able to escape this region. So that's why this is a black hole. And yeah, this is a aerial picture used to describe this black hole. This is so-called Penrose diagram. But you can look at the left-hand side here. So this is a aerial picture. I mean, when you draw a two-dimensional picture, you just have one dimension of space. So this is the x coordinate, okay? And this time coordinate is this vertical direction. This is a t coordinate, okay? And we always fix so that the speed of light is equal to 1. So you can see once your speed is equal to 1, then your slope is actually equal to 1. Okay, so these two directions will indicate the direction where light travels. Okay? And nothing travels faster than light. That will indicate that if you actually have a particle, it's going to move between these two 45-degree lines and move into the future. Okay? So this blue arrow here will represent the direction of a particle. And now this is the so-called Penrose diagram of the Schwarzschild black hole. Okay? And this rhombus-shaped area represents our universe. And this 45-degree line represents the horizon, r equal to 2m. Okay? And r keep on decreasing until this part here will correspond to r equal to 0. And that is a singularity. And this part here is where r is less than equal to 2m. Okay? And you can see that if you move from a point in the universe and you move in this direction, and somehow you enter this region, but you're restricted to move between these two 45-degree lines. Then once you enter this region here, you will never be able to escape. I mean, you can even make a computer game out of this. I think it will be fun to navigate a starship and then try to get close to the black hole without falling into it. Okay. But this is actually the Penrose diagram here. This is the black hole region, r less than 2m, and this is the horizon, r equal to 2m. Once you enter here, because your motion is restricted by this two 45-degree line, you will never be able to escape, and thus the black hole. And black holes, they were actually predicted by Michel and Laplace back in the 18th century. And it was really just based on a very simple assumption. They're assuming that the speed of light is actually finite. But this was unknown at that time. But if you just take this one here, you take Newtonian gravity, then you can actually make an argument that if a heavenly body is too dense, then light will never be able to escape from that heavenly body. Okay. But this also shows that solving this Einstein vacuum equation is actually more subtle due to coordinate invariance. You can see you can just write down a solution here which appear to be undefined. Okay? But really, you can just change the coordinate to make it well-defined. Okay? And this is so-called a gauge choice in solving Einstein vacuum equation. It's actually a big challenge whenever you try to solve the Einstein vacuum equation. But subsequently, so there are actually more exact or explicit solution of Einstein vacuum equation that were actually found. Okay, after Schwarzschild. Schwarzschild found his solution just a few months after Einstein announced this theory of general relativity. And among these solutions, one of the most important one is so-called the Kerr solution. It was actually discovered in 1968. Okay. This is again a black hole solution. Okay, but the one that Schwarzschild found is actually a steady black hole, meaning the black hole is just sitting there, not moving at all. But the Kerr solution actually represents a rotating black hole. Okay, so and you actually come out with a two parameter. You can see that in this Schwarzschild solution, there is a parameter here, that is this m here. Okay, of course, this is a result of solving ODE but we're going to see that this M here really just represents the mass of this black hole. And in the case of a rotating black hole, of course, you don't just have mass, but you also have angular momentum that measures how fast this black hole is rotating. And Kerr's solution is actually a black hole, rotating black hole solution. Okay? And the form is quite complicated, so I'll never try to write it down. But I hope I mean, this is going to be a metric tensor that has 10 components that satisfy the Ricci equal to 0 equation. And there are actually two important developments of black hole theory after this, well, or maybe some of them are running concurrently. One of them was Penrose's singularity theorem. Yeah, and in fact, Penrose was actually awarded the Nobel Prize 2 years ago because of this theorem. And in fact, Penrose was trained as a mathematician. He was actually trained as an algebraic geometer. Okay, so the first theorem is Penrose's singularity theorem. Okay, it tells you that black holes are generic. Okay, so in the case of Schwarzschild, so well, you have a horizon here. Okay, so this is the horizon, and once you enter the horizon, there's actually a singularity r equal to 0 in the future. And Penrose just tried to generalize this picture. So he has to actually generalize what it means by r equal to 2m for general space-time, and what it means by singularity for general space-time, because you don't have an explicit solution here. You want to say that black holes are actually generic. Okay, so in the case of Schwarzschild, you have r less than 2m horizon will lead to r equal to 0 singularity. But turns out Penrose realized that there's actually a way to reformulate this condition for general space-time. Okay, it turns out it's r equal to 2m in the case of Schwarzschild. You actually form a surface that is called a trap surface with this mean curvature or expansion less than 0. Okay, and he also has a way to formulate the singularity that corresponds to r equals 0, because that will actually correspond to the incompleteness of geodesics. But anyway, he was able to formulate this in a general space-time. So whenever your space-time has a surface, just like the r equal to 2m in Schwarzschild, okay, and then under some rather generic condition, there must be a singularity in the future. Okay, so this is quite a trip, because well, astrophysicists, they don't believe in the existence of black hole until much later, until they actually see, or not even see. They don't actually see some. They just see, some stars are rotating around a black mass in the center, and then they realize there must be something there that cannot be seen. But you can see that back in 1915, there's already Schwarzschild solution. That is a black hole solution. And in 1965, Penrose already proved that this is actually generic. As long as you have a horizon or a trap surface, then there's bound to be a singularity in the future. Okay. And well, the second theorem, they're actually a black hole uniqueness theorem. So the first theorem just tell you, I mean, this picture in Schwarzschild is actually quite generic. Okay. Because when you solve the Schwarzschild solution, you make a lot of assumptions, ansatz. Okay, you assume. So I mean, you figure maybe the singularity is just special because you choose a special coordinate. But Penrose singularity just tell you that black holes are actually generic. Okay, as long as you have a trap surface, you're going to have a singularity. But the second theorem actually tell you black holes are unique. Okay, so they sound quite contradictory. But this theorem can actually be formulated in terms of mathematics very easily. So what I mean here is, so this is actually a work I actually started back in the 1965, I think the first paper by Israel, and a series of paper results about black hole uniqueness. So this is really about the uniqueness of stationary solution of Einstein vacuum equation subject to boundary conditions. So you can formulate everything in terms of PDE theory. So it's like a Liouville theorem in PDE. Okay? So this is actually the case of Schwarzschild. Okay? I'm actually using a different picture. This is so-called gravity wheel. So inside here, you actually have a horizon, r equal to 2m. Okay? And when you go out all the way, it's actually asymptotically flat. I just mentioned that when r go to infinity, you actually approach a flat solution. Okay? So what it means is, well, let's assume it's stationary, okay, and then you become a three-dimensional picture because you can get rid of the t parameter. So you're solving a three-dimensional solution of the Einstein vacuum equation, and you assume some black hole boundary condition in the interior. Okay, so this is what I mean. So it's black hole uniqueness. So you have some black hole here, and then you assume some asymptotic flatness. Okay, some boundedness condition at infinity. Okay, and then you prove that the only solutions are the solutions that you actually found. Okay, so in particular, this among vacuum solutions, we're really talking about the uniqueness of Kerr. Okay, so Kerr is actually a global solution of vacuum, of Einstein vacuum solutions. And if you just prescribe the inner boundary condition that correspond to the black hole condition, and you prescribe that it's actually asymptotic flat, and you go ahead to solve the Einstein vacuum equation, you can end up with Kerr. Okay, so in a way, I mean, this equation is really quite well behaved because although you have non-trivial black hole solutions, but you do have a uniqueness, and everything's parameterized by mass and angular momentum. Okay? Yeah, this is just another picture that people use to describe this kind of, for example, Schwarzschild. I mean, you have a horizon here. If you move too close to the horizon, and then you just fall down, and you will never be able to escape.
Question.
Yes?
Stationary, you mean time independent?
Yeah, I mean, it's you have to formulate in a way that you allow rotation. So it just keep on repeating itself. Okay, so when you write down when you write down the metric, you still have a t coordinate there. Okay, but it just repeats itself. So that's the stationary, as opposed to static. In the case of static Schwarzschild, it just doesn't move at all. Okay.
So do you have explicit solutions which depend on time?
I'm sorry?
Explicit solutions that depends on time.
Yeah. Well, there are explicit. Well, okay. Explicit solutions. It depends on how you do have some explicit solutions. Okay. But if you're talking about global solutions, okay, of global solutions of Einstein vacuum solution, okay, then I think it's just Kerr. I mean, and you ask for explicit. I mean, of course, you can solve PDE. I'll talk about it later. You can solve a PDE and you try to describe complete solutions, but none of them can actually be written down explicit. And there are actually a lot of other explicit solutions, but they are not asymptotic flat, and they are not black holes or not black hole solutions.
But you mentioned future black hole.
Yeah.
So that means like you don't have explicit examples. Because that happens in the future.
Well, you can actually write down things quite explicitly near the black hole. But I'm just talking about if you actually want some global space, global solutions, then you don't really have any explicit solution except for Kerr. Okay. Right. So you can see that it's Einstein vacuum equation and this equation for mean curvature. They're sort of intertwined. So you can see that in the case of geometric PDEs, two of the most studied one, there are actually these two equations. That is Einstein equation for metric G and the minimal surface equation for surface sigma. And in a way that there are actually, well, there is a great advancement towards understanding these PDEs since then. But but we actually need more solutions. As of 1980s, all known global solutions of Einstein vacuum solutions, they are actually explicit solutions based on some symmetry assumptions. Okay, so you can make some assumption. I mean, in the case of Kerr, not just stationary, you actually have to make more assumptions in order to solve it explicitly. But we know not every space-time satisfies the assumptions of these solutions. So you need to have a way to construct more general solutions. So we need a more general way to solve the Einstein vacuum equations, and in particular to obtain dynamical solutions. So there comes this kind of initial value, or physicists like to call Hamiltonian formulation of the Einstein vacuum equation. Okay? So this is formulated as an initial value problem. Okay? So in this case, well, you're solving a four-dimensional space-time. Okay? And of course, the unknown is the Lorentz metric. But what you do is you start with some t equal to 0. Okay? But when t equals 0, that will actually correspond to a three-dimension, because you impose one condition. This is three-dimensional one. And so this is going to be a three-dimensional manifold. And you can just think of a three-dimensional manifold with a given initial function and a given first derivative that is called a momentum. Okay? And you're trying to solve this second-order partial differential equation. Okay? So this is time direction again. It's initial value formulation. Okay? So the solution actually breaks down into two steps. Okay? So first of all, you want to construct initial data set. Okay? Because now this is a PDE here. I mean, you just take any arbitrary slice here as initial data. There are actually equations coming from the Einstein vacuum equation that has to be satisfied on this initial data. Okay? So this is going to be a three-dimensional manifold. Okay? And you're solving the metric. So you're going to look at the metric, initial metric on the three-dimensional manifold. And this K0 here will basically correspond to the first derivative of this, this initial metric. Okay? And you want to go ahead to solve this second-order equation of Einstein vacuum equation. And in particular, in this case, this M dot here is actually a Riemannian manifold now, instead of Lorentz manifold. And the second step, this is actually formulated by Schocker, Bruha, and York back in the 1970s. So the step two is you solve the evolution equation. Okay? So now you can actually choose a particular coordinate system. Then you can rewrite the Einstein vacuum equation in this form. So this is actually a wave operator. This box operator is actually it's just a nonlinear version of the wave operator that you've seen. But it's a nonlinear one. And then you just evolve this G0 here, subject to the initial condition. So you're given, this initial G0 here, an initial first derivative of G that is denoted as K0, K0 here. And then you solve this wave-like equation. Okay, so this provides a way to generate more general solutions. So now you just need initial data, and you just try to solve this equation to see. But of course, you want to have some global solution. You want to be able to see time go to infinity. And during this time, there's also a way to define the total mass for this initial data here. So this is M0, G0, K0 here. So as I just mentioned, you can see that in the Schwarzschild solution, there's actually an M over there, and that represents the mass of this Schwarzschild black hole. Okay, but we need more general initial data here. So you have to be able to make sense of this mass of this kind of general initial data. So this is actually work by Arnold Waite, Desir, and Misner. So they define the so-called ADM mass for this kind of initial data. Okay, and if you calculate this on Schwarzschild, you're just going to recover this M here. And after decades of efforts, this passing mass theorem was actually established by Shen Yao and Witten in the 1980s. Okay? it actually shows the total ADM mass of an isolated gravitating system cannot be negative. This is actually quite essential because that without this, the system could be actually unstable. And it's kind of surprising to physicists because their proof actually relies on the theory of minimal surface in three manifold. Okay, so and it's actually an un-Riemannian manifold. So again, this kind of connection between the Einstein equation and this minimal surface equation was actually used in the proof. And the proof was actually difficult because the total ADM mass is actually defined as actually an integral at infinity. In the sense that you have this system here, but you can only measure the mass at infinity when it's actually asymptotically flat, when you're actually close to the Minkowski space. So as opposed to what we usually think, I mean, whenever we think about mass, we usually think about there's some mass density here, and you can just integrate this mass density in order to get a total mass. But this is not the case for this ADM mass. It's actually defined as a flux integral at infinity. And this is because by Einstein's equivalence principle, gravitation has no density. Okay? This is again goes back to this coordinate invariance, because everything is expressed in terms of this Lorentz metric. And if you work with for example, wave equation, the way to construct density is to take first derivatives of your field and then form some quadratic expression. But the first derivative of the Lorentz metric doesn't make sense locally, because you can actually choose any coordinate system, choose a particular coordinate system to make the first derivative vanish at any point you like. Okay? And this is actually formulated by Einstein, and it's called Einstein's equivalence principle. So gravitation has no density. And this proof actually ushers in a golden age of mathematical relativity. So there are actually a lot of applications of powerful tools, from geometry analysis to the study of general relativity. So let me just highlight some of the later development related to this Einstein vacuum equation and black holes. Okay? So for example, in the 1990, early 1990, 91, 1991, I think, there was Christoph Kleinerman. They actually proved the global stability of Minkowski space-time. So this is under this kind of initial value formulation. So you just take R3 and you perturb a little bit, okay? And then you evolve by the Einstein vacuum equation, and you can prove that global existence, and you will actually converge back to the Minkowski space-time. So that shows the Minkowski space-time is actually globally stable. And also, Penrose's theorem tells you that once you have trapped surface, you're going to have a singularity or a black hole. But the mechanism of how trapped surface arises was actually not known. So there was actually Sheng Yao that actually proved the existence of trapped surface on initial data set. And there's also Christoph's work that in 2008 that he actually showed that a trapped surface it can be actually formed by the Einstein vacuum equation. And very recently, there are a lot of work about black hole stability. Okay? So we already know this black hole uniqueness. And in fact, based on this black hole uniqueness theorem, and this is something that physicists like really, I mean, once you have some uniqueness, and therefore you can try to model everything around this uniqueness results. But of course, the question is that whether this kind of approximation is stable or not. You just do all kinds of calculations using this model, but whether this calculation they're actually reliable or not. And these actually rely on this kind of global stability. Okay, so recent work of Kleinerman and Zeftel proved that Kerr black hole stability for small angular momentums. And this is again based on earlier work of Dahlmeier, Hosekel, and Rodyansky about the linear stability of Schwarzschild. Yeah. And I'd like to say a little bit about my own work. So my own work is actually related to this kind of definition of mass and angular momentum. So after the proof of passing mass theorem, so Penrose actually proposed a list of major unsolved problems of general relativity. And in fact, the number 1 and number 2 problem are actually about defining mass and angular momentum of a finitely extended region. Okay? So I just mentioned that this ADM mass is actually defined at infinity. You really have to go out, and therefore you're really dealing with a total mass. But in many cases, you can imagine that actually you need to understand mass or angular momentum on a finitely extended region. Okay? I mean, in fact, I can just show you this picture that I'll talk about later. This is actually two black hole merger. This is actually, sort of detected in the first gravitational wave detection back in 2015. So you have two black holes that are actually rotating about each other. And of course, it will be very interesting to know what the mass of each of the black hole is, and also the total mass of this system. Okay, so at that time, I was proposed this definition of mass and angular momentum on a finitely extended region. Instead of defining an infinity, you want to be able to define it for any finite region. And this is actually called quasi-local mass and quasi-local angular momentum. And again, the challenge actually stems from Einstein's equivalence principle, which implies that there's no localized density of gravity. So once you have a mass density, then just go back to calculus. You can just integrate your density and you get a total mass. But the difficult part is that there's no density. Yes? Okay. So we have some recent progress made by myself and my collaborators, Pauline Chen, Yikai Wang, and Xintong Yao. And this work actually has led to a solution of a long-standing super translation ambiguity that was since the 1960s. So I'd like to just say a few words about this recent progress. So that is this resolution of this super translation ambiguity. Okay, so there was an ambiguity that was found back in the 1960s. But what is this ambiguity? This ambiguity actually concerns the definition of angular momentum for distant observers. Okay, this is actually observers. In particular, the amount of angular momentum carried away by gravitational wave. Okay, so for example, in this case, you have two black holes. They are actually rotate about each other, and they eventually merge into a single black hole. And there's a gravitational wave release. And you want to know the amount of angular momentum carried away by gravitational wave. So it's basically the initial angular momentum and the angular momentum after the merge. While the radiated mass is well defined by the bounding mass. Okay, so if you look at the announcement in September 2015 of the first detection of gravitational wave, they actually talk about the event they observe correspond to a binary black hole merger. So one of the black hole actually has mass 36, the other one has 29. Okay? And then when they merge together, they end up with a black hole with mass 63. And that is because the mass there is actually well defined by the bounding mass. That was actually back in 1962. However, there also was a definition of angular momentum back in the 1960s. But the existing definition of angular momentum actually leads to discrepancies measurement by different observers. Okay? So in this case, again, you have a system here. You have two black holes that are rotating about each other. And you set up a coordinate system, and you have a definition of angular momentum. And you just calculate the angular momentum radial wave. But it turns out it depends on the coordinate. Okay? So if you change a different coordinate system here, you end up with a different amount. Okay? And in fact, we can prove that. Just give me any real number, and I can give you an observer that will observe this amount of angular momentum radiation. Okay? So that is called the super translation ambiguity since the 1960s. But our theory of quasi-local angular momentum actually offers a solution. It actually provides a new definition of angular momentum that is a super translation invariant, in the sense that it is actually independent of observers. Okay, so this kind of goes back to this Lorentz norm there. I mean, if you don't use the right definition, if you just emphasize an x or t, different observers who have different space, different time. But if you find the right Lorentz norm, then different observers actually observe the same Lorentz norm. Yeah, so this is actually a picture. This is a picture from Quantum magazine. About this work here, and so this is quite nice because this in the middle of here, this is like a dumbbell, but it actually represents a binary black hole system. So you have actually two black holes, and they're actually rotating about each other. And these eyes will correspond to observers. Okay, so you have different observers looking at this binary black hole merger. Okay, so they're rotating. And each one of them, if you have given a definition of angular momentum, and each one of them can do the calculation of this angular momentum. But the existing definition has actually ambiguity for each of these eyes. You come up with a different answer. But if you use the definition that we come up with, then you actually will arrive at the same answer. And our work actually rely on, quite interesting, rely on this theory of isometry embedding in pure mathematics. And in a way that we identify some correction term. And that correction term actually came from solving this isometry embedding equation. Yes?
These four eyes are for observers.
Yeah, you can look at these from different angle. And you could come up with different, if you use the existing definition, you come up with different answer. But if you use our definition, you come up with the same answer. Right? Okay. I know this is the end of the talk, so I don't want to talk about too much. I want to show you some pictures and maybe some future outlook and maybe make some connections to astrophysics. Because as I say, you can see black holes. They were actually predicted in the 18th century, and the first solution was found in 1915, and 1965, Penrose already proved that it's actually generic. But it wasn't really, astrophysics, they don't really believe it until much later, until they can see, this black mass in the center and everything's rotating about this invisible mass. And but it was actually back in 2022 to really see it. Okay, so this is actually the first image of black hole was actually observed by the Event Horizon Telescope. So to see is to believe. So this is not until 2022 do you really see the image of the black hole. So, but you can see there are actually, there are actually some major advancement in astrophysics. Yeah. So, for example, in 2015, there's actually the first detection of gravitational wave. Okay? And then in 2022, you can actually see the image of the black hole. In a way that we were surprised that the shape of the black hole is actually wrong. For us mathematicians, we've been assuming it's wrong for a long time because in the case of Schwarzschild solution, it's actually wrong there. But I think for astrophysics, it's just not clear what the shape of the black hole should be until you see a circle in the center of the black. Right, so I think the future outlook is we should try to understand better of this in a strong field regime in a way that so far most of the understanding focus on this kind of isolated system. So in the case of Kerr, it's really a black hole in the center and asymptotic flat. But we still don't know much when you're actually getting very, very close to the black hole. We know very, very little about these so-called binary systems. Okay? So in particular, this is the kind of binary system I was talking about. You actually have, and as I said, this is the one that was observed, that was detected in the first detection of gravitational wave in 2015. There's actually a simulation by LIGO. You can take a look. Yeah, and then so you have two black holes. They are rotating about each other, and then eventually they merge into a single one. Okay? And so far, this part here is actually computed just by numerical calculation. There are very, very little mathematical theory to support this part here. But this part after the merge, okay, because it become a single black hole. So the theory of Kerr, and then they have actually been used. This is called the ring down region, okay? But of course, this is a case, this is a very interesting case. But so far, as I say, we don't really have any model, explicit model for this kind of binary system. So all research in this part actually done by numerical calculation, a very few understanding of this kind of system. And a very exciting one is actually this so-called EMRI. And I think we'll be able to, maybe 2028, there's going to be a new generation of gravitational wave detector. LISA, there's a space detector. Okay? And it's very hopeful that we can, I think this binary system is still too hard. Okay? But this is so-called extreme mass ratio in spirals. So this is a case that this is something that we can really, theory, we can make some, we can make some advancement in theory, and maybe we'll be able to compare with the data observation. So what it means is the following. So extreme mass ratio, it means that you actually have a super massive black hole here. So this is huge. But you also have a small size black hole that is rotated about this supermassive black hole. And this is a case when a lot of theory can be done, because you have two parameters, the mass ratio, you can actually play around here, okay? But this is, LISA, we're expected to, they're expected to observe this so-called EMRI in just a few years. Okay, so I think I'll just stop my talk there. Thank you.